Hello and welcome back to the another class of fundamentals of particle and fluid solid processing. In the last class we had the introduction of filtration and we have seen that there are two different processes of filtration and sometimes they merge also in a certain process. These two filtrations technique, which were the cake filtration and deep end filtration, those we have seen that deep bed filtration, we have seen that those also sometimes coincide or have there exist in a certain process. Now we have seen that in cake filtration a cake deposition occurs on the top of the filtration media or the filter media, and in deep bed filtration what happens is that particles stuck into the pores of the or penetrates into the pores of the filter media, and then the pressure builds up, and we have also seen that how to recover this filter media by back washing or the back flushing with a wash liquid. Okay. Now the point is that if we consider this cake filtration, the reason I mentioned that in cake filtration we can recover easily the solid particles, because in our case solid particles are of more importance because we are dealing with the fundamentals of particles and fluid solid processing. Now in deep bed filtration the thing that happened was that we did not bother about the solid particles, we cared more about the filter media. So focusing on the cake filtration, and we have mentioned that this cake is basically consist of fine particles of certain voidage. Now since this is a packed bed of particles, quite clearly there will be the voidage, okay, or the void spaces through which the filter media can pass through, the filtrate can pass through, suspension can pass through. Okay. So now if we consider that this cake is incompressible, which means this cake characteristic does not change with the pressure applied. Okay. And what does this mean? Which means that the voidage of this cake is constant, because with increasing pressure, if the particle orientation and particles does not compress against each other, so that void space squeezes or it alters the bed orientation, these are not loosely packed particles. Okay. So in that case we can consider that the cake that has been formed on the top of the surface media or the filter media is of incompressible nature. So if we consider this incompressible cake, and for the time being you also consider that the filtration is happening mainly due to this cake that has been formed. Okay. So because this contributes the major portion of this resistance, let us focus initially on this part only. Although there is the resistance by the filter media itself is there, we will incorporate that influence in a later stage. But for the time being we consider that this filtration pressure drop or the pressure drop that is required to have a particular rate of filtration is essentially dictated by the flow through the resistances happening due to the flow through this cake or the porous media. So in that case we know the pressure drop and the velocity relation. Okay. So if we write the full fledged Argan equation, it has two components. One is indicating the laminar contribution or the viscous contribution, the other is the inertial contribution. Now the particle size, range, the type of fluid, all these things, the size distributions that are typically used in industrial scale, it has been seen that this contributes towards only the laminar flow part. That means the laminar flow occurs during this filtration process, which means we can safely neglect this part. Okay. And then if we consider that in that process the particle properties are constant, okay, which means the voidage does not vary with time, the particle size is not changing with time, because there is a pressure drop across this bed, and in industrial scale you can understand that there is a tons of barrels of liquid that is flown or that is handled at a time. So there is a huge pressure drop, or the pressure drop that is required for this filtration or to pass this fluid through a filter media with time. Now with such pressure there are chances that the particles, the sizes, if it is bigger in size, it can break, the size change during this attrition, collisions and etc. But we consider that particle size is also constant, because if it becomes very finer, that size does not change much. So these are the logical conclusion we can make, that this cake resistance is then becomes a constant parameter at a certain point of time. Okay. This resistance, if we define the resistance, specific resistance rather, let us define this RC term as the specific resistance. Although the resistance changes with time, this specific resistance remains same, because it has only the parameters that consist of the solid particle characteristics, and we consider these are of constant values. The voidage is constant, the size of the particle is constant. If we define the specific resistance in this manner, then this top expression becomes that del P by H is equals to specific resistance multiplied by the viscosity and velocity. Okay. Now, if we consider that V is the volume of filtrate passing the filter media at in any time t, then dV by dt is the instantaneous volumetric flow rate, and if that is so, then the superficial filtrate velocity, we know the instantaneous volumetric flow rate divided by the cross sectional area, say that is A in this case. That becomes the superficial velocity in that Argand expression becomes 1 by A dV by dt, because now we are trying to estimate this parameter del P. This RC value we can know if the solid properties are known. Okay. This U we are looking at it right now. Mu comes from the filtered viscosity, which is a measurable quantity. So now if we try to have it quantified, the superficial filtered velocity, okay, the point you can now think of that with each unit of this volume of filtrate that is flowing or passing through the filter bed is depositing certain amount of solids on the filter media, which means it contributes to the certain volume of the cake, each unit of the suspension that is flowing through the cake. So now if we think of that the volume of cake formed by the passage of this unit volume of filtrate as phi, then this phi is nothing but H A by V, where H is the height of the cake, A is the cross sectional area, V is the volume of filtrate passing at any time t, isn't it? That the amount of filtrate that is passing through the filter media creates or forms a phi amount of cake material on the top of this filter. We knew this expression from argon equation. We now have phi value. Okay. So, which means now we can have this dV by dt value as this one if we link all the three expressions. Because del P by del H is equals to this value, which is RC mu 1 by A dV by dt. You find dV by dt and you would find that there is a expression H by V. To make it, you can create, you can multiply the numerator by A and do the A square. So, eventually by linking these three expression, we can find the instantaneous volumetric flow rate of this filtration process. This in the numerator we have A square minus del P divided by specific resistance divided by viscosity divided by volume of cake that has been formed multiplied by this V, which is the volume of filtrate that is passing at the instant of time t. So, by looking at this expression, what you can derive is that you have filtration rate is proportional to the pressure drop and inversely proportional to the volume of filtrate that is passing through the time t, and inversely proportional to the viscosity mu, which means the filtrate medium viscosity, if the filtrate suspension viscosity increases, this rate goes low and low. As the filtration media area, available area increases, the filtration rate increases to the square of the available surface area, drastically increases. As you increase the pressure drop across this bed, the filtration rate increases proportionately. As the thickness, which is quantified by phi, because this is H A by V, the volume of the filter medium or the cake material, as it increases, filtration rate goes lower, it decreases. So, this is a very important relation or expression that you have to remember for the filtration rate calculation. So, there can be under this cake filtration, as I mentioned earlier in the last class, that if you appreciate the scenario that you have to have a constant rate of filtration, then the pressure drop across this filter cake is directly proportional to the volume of passing filtrate. It increases, the pressure drop you have to increase with time to have the desired amount of or the desired volume of filtrate that should pass through, that is the constant rate filtration. Or in other case, if you keep the constant pressure drop, which is the most frequently occurred scenario, that we operate the filtration process under a certain pressure drop, then we see that this value, this filtration rate, basically this amount or the volume of filtrate that is passing, that would decrease in order to have the same rate. Now, if we have this constant pressure drop filtration, this scenario, as I said, this is the most frequent scenario, what we can see that this del P is constant in such cases. Okay, and this dV by dt is inversely proportional to this volume of the filtrate V. If we integrate this, we get an expression T by V is equals to C1 V, where C1 is this expression RC mu phi divided by 2a square multiplied by del P. So, which means there are two types or two scenario can happen. One is the constant rate filtration, where dV by dt is constant. Okay, if you either you can have this rate is constant, and then if you desire so, your pressure drop this increases with the amount of the volume of the passing filtrate. In other case, if you have your control on the pressure drop, you fix the pressure drop, then this is the relation that the filtration rate is inversely proportional to the volume of passing filtrate, and T by V is C1 V, where C1 the integrating constant is this value. That means this is the time that is required to have a certain volume of filtrate to pass through the filter media under a constant pressure drop condition. This relation gives that required time, the T by V, this calculation. For constant pressure drop filtration, say you were asked about what is the time that is needed to filter this much volume of the suspension under a constant pressure drop scenario. This expression would give you that result. But this is the case where we have only considered the cake as the effective filter medium or the filter portion. We did not consider the resistance to the filter itself. If we consider that, that means, as I mentioned, that we have total pressure drop, that is the pressure drop resulting due to the medium, and this pressure drop across the cake that we have just calculated, or we have seen that scenario only. If we name this, that minus del P, the overall pressure drop, is basically the del P due to medium, which is M, and through cake, which is C as superscripts, sorry, subscripts. Okay. Then we can write the del P expression considering the medium as a packed bed of certain depth Hm and resistance Rm, which follows the Koenig-Karman expression. If these assumptions are satisfied, then we can write the total del P of this much. In the last couple of slides, we have seen this del P is this value, this plus this. We did not consider this part, the medium part. It was not considered earlier. But with the introduction of consideration for pressure drop across the medium, which we consider that the medium exhibit or medium gives us a pressure drop that is equivalent to a packed bed of depth Hm that has a resistance of Rm, and since the flow is in laminar condition, we consider that it follows that Koenig-Karman expression. If it happens, then we have seen this expression that minus del P is equals to 1 by A dV by dt multiplied by the summation of Rm mu Hm plus Rc mu Hc. I hope this expression is clear. This is the total pressure, because if you look at this previous slide, this expression 3 that we have got was for the cake. Now this was the terms Rc mu u for del P by H. Okay. So similarly here we have Rc mu Hc. Now expressing this medium resistance, which is typically done, we consider this medium resistance as an equivalent thickness of cake, because we have assumed that filter media is a equivalent packed bed of height, certain height. Now we further assume that this packed bed is of equivalent cake thickness, that is depositing on the filter media. Then this Rm Hm, we equate that with the cake resistance multiplied by a equivalent height of the cake. So which means this filter media resistance, we consider that this filter media resistance is of equivalent to the cake resistance having height h eq. And this cake specific resistance, we know that this is Rc. And since phi, the amount of cake, is equals to HA by V, this Heq is basically phi Veq by A, where V is the equivalent filtrate that must pass through the filter to create a equivalent height of cake Heq. Isn't it? Because phi is HA by A. Now we are considering that the filter media is exerting a Heq thickness of cake specific this resistance. If that happens, then this EQ VEQ is basically volume of filtrate that must pass through the filter medium to form a cake of HEQ, and this quantity depends solely on the suspension and filter media properties. So, which means we had this expression, okay, and then we replace that RMHM with RCEQ, where HEQ is basically this function. We replace all these parameters in this expression and find the rate of filtration in terms of del P and the overall resistance. That 1 by A dV by dt is equals to minus del P A divided by RC mu V plus VEQ multiplied by phi. So, this is the expression when we consider the resistance, the overall resistance is resistance due to the filter medium and the cake that is depositing on top of the filter medium. So, we have the filtration rate expression for a filtration process, cake filtration process specifically, with constant pressure condition having the overall resistance that includes the filter medium resistance and the cake medium resistance. If we integrate this expression for constant pressure, we have the expression for time versus volume of filtrate. That this time versus volume of filtrate expression is particularly of importance when you have to find that what is the time required to process or to filter this much of filtrate or this amount of filtrate under the constant pressure condition of certain value. The other properties are known to you. In such case, you can use this expression and find out the time required, or the other way, you can find out that at this particular time or at this much time I can have this much volume of filtrate to as a process. So, I hope till this point it is clear to you. So, what we covered today is that considering the incompressible cake, flow through incompressible cake, its pressure drop, okay, how it varies, we knew that. We find what is the time required to process a certain volume of filtrate when we considered the resistance in the filtration is only due to the cake formation, and in the next step we included the filter medium resistance in that cake resistance as well to have the total resistance during, or more practically during this filtration process, and the time versus volume of filtrate expression in that case. In the next class, we will be dealing with couple of problems to clear this or to better understand these theoretical expressions and its application. Till then, thank you for your attention.